Hi, hello there. Welcome to Transport Layer. The transport layer is where, as the name implies, data is transported from one host to another. This is where your network really gets moving. The transport layer uses two protocols, TCP and UDP. Think of TCP as getting a registered letter in the mail. You have to sign for it before the mail carrier will let you have it. This slows down the process a bit, but the sender knows for certain that you received the letter and when you received it. UDP is more like a regular stamped letter. It arrives in your mailbox, and if it does, it is probably intended for you, but it might actually be for someone else who does not live there. Also, it may not arrive in your mailbox at all. The sender cannot be sure you received it. Nevertheless, there are times when UDP, like a stamped letter, is the protocol that is needed. This topic dives into how TCP and UDP work in the transport layer. Let's get started. This video lecture is entitled Transport Layer. At the end of this video lecture, you should be able to compare the operations of transport layer protocols in supporting an end-to-end communication. The video lecture is divided into several segments. This includes transportation of data, TCP Overview, UDP Overview, port numbers, TCP Communication Process, reliability and flow control, and UDP communication. Transportation of data. Let's start with the role of the transport layer. Application layer programs generate data that must be exchanged between the source and destination hosts. The transport layer is responsible for logical communications between the applications running on different hosts. This may include several services such as establishing a temporary session between two hosts and the reliable transmission of information for an application. As shown here in the figure, the transport layer is the link between the application layer and the lower layers that are responsible for network transmissions. The transport layer has no knowledge of the destination host type, the type of media over which the data must travel, the path taken by the data, the congestion on the link, or the size of the network. The transport layer includes two protocols, TCP or the Transmission Control Protocol and UDP or the User Datagram Protocol. Transport layer responsibilities. Tracking individual conversation. Segmenting data and reassembling segments. Adds header information. Identify, separate, and manage multiple conversations. Uses segmentation and multiplexing to enable different communication conversations to be interleaved on the same network. Let's start with tracking individual conversations. At the transport layer, each set of data flowing between the source application and the destination application is known as conversation and is tracked separately. It is the responsibility of the transport layer to maintain and track these multiple conversations. As illustrated on this diagram here, a host may have multiple applications that are communicating across the network simultaneously. So you've got email, instant messaging, multiple web pages, online video chatting, and streaming video. Most networks have a limitation on the amount of data that can be included in a single packet. Therefore, data must be divided into manageable pieces. Next would be segmenting data and reassembling segments. It is the transport layer responsibility to divide the application data into appropriately sized blocks. Depending on the transport layer protocols used, the transport layer blocks are called segments or datagrams. The figure here illustrates the transport layer using different blocks for each conversation. The transport layer divides data into smaller blocks. It could be segments or datagram that are easier to manage and transport. Next would be add headers information. The transport layer protocol also adds header information containing binary data organized into several fields to each block of data. It is the values of these fields that enable various transport layer protocols to perform different functions in managing data communication. For instance, the header information is used by the receiving host to reassemble the blocks of data into a complete data stream for the receiving application layer program. The transport layer ensures that even with multiple applications running on a device, all applications received the correct data. Next would be identifying the applications. The transport layer must be able to separate and manage multiple communications with different transport requirement needs. To pass data streams to proper applications, the transport layer identifies the target application using an identifier called port number. As illustrated in the figure, each software process that needs to access the network is assigned a port number unique to that host. An example of those port numbers includes 110 for email, port 80 for HTTP or HTML page, and port 531 for internet chat. Port is also known as socket. Conversation multiplexing. Sending some types of data, example streaming video, across the network as one complete communication stream can consume all the available bandwidth. This would prevent other communication conversations from occurring at the same time. It would also make error recovery and retransmission of damaged data difficult. So as shown here in the figure, the transport layer uses segmentation and multiplexing to enable different communication conversations to be interleaved on the same network. Error checking can be performed on the data in the segment to determine if the segment was altered during transmission or while in transit. Next would be the transport layer protocols. IP is concerned only with the structure, addressing, and routing of packets. It does not specify how the delivery or transportation of the package takes place. The transport layer protocols specify how to transfer messages between hosts and are responsible for managing reliability requirements of conversation. The transport layer includes TCP and UDP protocols. Different applications have different transport reliability requirements. Therefore, TCP IP provides two transport layer protocols as shown here in the figure. So you've got the TCP and UDP mapped with the IP on the internet or the network layer. Now, there are applications or protocols that can be classified as TCP or UDP. An example of those, FTP, HTTP, SMTP, and DNS are said to be classified under TCP. DNS and TFTP would be part of the UDP. IP is concerned only with the structure, addressing, and routing of packets from original sender to final destination. IP is not responsible for guaranteeing delivery or determining whether a connection between the sender and the receiver needs to be established. TCP is considered a reliable, full-featured transport layer protocol, which ensures that all of the data arrives at the destination. TCP includes fields which ensure the delivery of the application data. These fields require additional processing by the sending and receiving hosts. So take note that TCP divides data into segments. TCP transport is analogous to sending packages that are tracked from source to destination. If a shipping order is broken up into several pieces or packages, a customer can check online to see the order of the delivery. TCP provides reliability and flow control using these three basic operations. Number one, number and track data segments transmitted to a specific host from a specific application. Second is acknowledge received data. Third would be retransmit any unacknowledged data after a certain amount of time. Sequence data that might arrive in wrong order. Send data at an efficient rate that is acceptable by the receiver. In order to maintain the state of conversation and track the information, TCP must first establish a connection between the sender and the receiver. This is why TCP is known as connection-oriented protocol. Now, the figure here shows how TCP segments and acknowledgments are transmitted between the sender and the receiver. User Datagram Protocol, or UDP. UDP is simpler transport layer protocol than TCP. It does not provide reliability and flow control, which means it requires fewer header fields. Because the sender and the receiver UDP processes do not have to manage reliability and flow control, this means UDP datagram can be processed faster than TCP segments. UDP provides the basic functions for delivering datagrams between the appropriate applications with very little overhead and data checking. So take note that UDP divides data into datagrams that are also referred to as TCP segments. UDP is a connectionless protocol. Because UDP does not provide reliability or flow control, it does not require an established connection. Because UDP does not track information sent or received between the client and the server, UDP is also known as the stateless protocol. UDP is also known as the best effort delivery protocol because there is no acknowledgement that the data is received at the destination. With UDP, there are no transport layer processes that inform the sender of a successful delivery. So UDP is like placing a regular, non-registered letter in the mail. The sender of the letter is not aware of the availability of the receiver to receive the letter, nor is the post office responsible for tracking the letter or informing the sender if the letter does not arrive at the final destination. Now, the figure here shows how UDP datagrams are being transmitted from the sender to the receiver. The right transport layer protocol for the right application. So some applications can tolerate some data loss during transmission over the network, but delays in the transmission are unacceptable. For these applications, it's a better choice because it requires less network overhead. UDP is preferable for applications such as voice over IP or VoIP. Acknowledgement and retransmissions would slow down delivery and make the voice conversation unacceptable. UDP is also used by request and reply applications where the data is minimal and retransmission can be done quickly. For example, domain name services or DNS uses UDP for this type of transaction. The client requests IPv4 and IPv6 addresses for a known domain name from DNS server. If the client does not receive a response in a predetermined amount of time, it simply sends the requests again. For example, if one or two segments of a live video stream fail to arrive, it creates a momentary disruption of the stream. This may appear as distortion in the image or sound, but may not be noticeable to the user. If the destination device had to account for lost data, the stream could be delayed while waiting for the retransmission, therefore causing the image or sound to be degraded. In this case, it is better to render the best media possible with segments arrived or received and forgo reliability. For other applications, it is important that all data arrives and that it can be processed in its proper sequence. For this type of applications, TCP is used as the transport protocol. For example, applications such as databases, web browsers, and email clients require that all data that's sent arrives at the destination in its original condition. Any missing data could corrupt a communication, making it either incomplete or unreadable. For example, it is important when accessing banking information over the web to make sure all the information is sent and received correctly. Application developers must choose which transport protocol type is appropriate based on the requirements of the applications. Video may be sent over TCP or UDP. Applications that stream stored audio and video typically use TCP. The application uses TCP to perform buffering, bandwidth probing, and congestion control in order to better control the user experience. Real-time video and voice usually use UDP, but may also use TCP or both UDP and TCP. A video conferencing application may use UDP by default, but because many firewalls block UDP, the application can also be sent over the TCP. Applications that streams stored audio and video use TCP. For example, if your network suddenly cannot support a bandwidth needed to watch an on-demand movie, the application pauses the playback. During the pause, you might see a buffering message while TCP works to reestablish the stream. When all the segments are in order and a minimum level of bandwidth is restored, your TCP session resumes and the movie resumes playing. So the figure here summarizes the differences between the UDP and TCP. Again, UDP can be used on VoIP or IP telephony with DNS. Required protocol properties like fast, low overhead, does not require acknowledgments, does not resend lost data, and delivers data as it arrives. Now for TCP, this is said to be reliable, and these are used by SMTP or IMAP for email and HTTP or HTTPS. So required protocol properties would be reliability, it acknowledges data, resends lost data, and delivers data in sequence order. TCP Overview. In the previous topic, we learned that TCP and UDP are the two transport layer protocols. This topic gives more details about what TCP does and when it is a good idea to use it instead of UDP. To understand the differences between TCP and UDP, it is important to understand how each protocol implements specific reliability features and how each protocol tracks conversations. In addition to supporting the basic functions of data segmentation and reassembly, TCP also provides the following services. Establishes a session. TCP is a connection-oriented protocol that negotiates and establishes a permanent connection or session between the source and destination devices prior to forwarding any traffic. Through session establishment, the devices negotiate the amount of traffic that can be forwarded at a given time, and the communication data between the two can be closely managed. Ensures reliable delivery. For many reasons, it is possible for a segment to become corrupted or lost completely as it is transmitted over the network. TCP ensures that each segment that is sent by the source arrives at the destination. Provides same order delivery. Because networks may provide multiple routes that can have different transmission rates, data can arrive in the wrong order. By numbering and sequencing the segments, TCP ensures segments are reassembled into the proper order. Supports flow control. Network hosts have limited resources, example, memory and processing power. When TCP is aware that these resources are overtaxed, it can request that the sending application reduce the rate of data flow. This is done by TCP regulating the amount of data the source transmits. Flow control can prevent the need for retransmission of the data when the resources of the receiving hosts are overwhelmed. For more information on TCP, search the internet for the RFC 793. TCP Header. TCP is a stateful protocol, which means it keeps track of the state of the communication session. To track the state of a session, TCP records which information it has sent and which information has been acknowledged. The stateful session begins with a session establishment and ends with a session termination. A TCP segment adds 20 bytes or 160 bits of overhead when encapsulating the application layer data. The figure here shows the fields in a TCP header. So you've got source port, destination port, sequence number, acknowledgement number, header length, control bits, reserved, window, urgent, checksum, options, and application layer data. Size varies. So the table here identifies and describes the 10 fields in the TCP header. Applications that use TCP. TCP is a good example of how the different layers of TCP IP protocol suite have specific roles. TCP handles all tasks associated with dividing the data stream into segments, providing reliability, controlling data flow, and reordering segments. TCP frees the application from having to manage any of these tasks. Applications like those shown in the figure here can simply send data to the transport layer and use the services of TCP. So protocols like HTTP, FTP, SMTP, SSH are all TCP. UDP Overview. UDP Features. This topic will cover UDP, what it does, and when it is a good idea to use it instead of TCP. UDP is a best effort transport protocol. UDP is a lightweight transport protocol that offers the same data segmentation and reassembly as TCP, but without TCP reliability and flow control. UDP is such a simple protocol that it is usually described in terms of what it does, not do compared to TCP. UDP features includes the following. Data is reconstructed in the order that it is received. Any segments that are lost are not resent. There is no session establishment. The sending is not informed about resource availability. For more information on UDP, search the internet for the RFC on UDP. UDP Header. UDP is a stateless protocol, meaning neither the client nor the server tracks the state of the communication session. If reliability is required, when using UDP as the transport protocol, it must be handled by the application. One of the most important requirements for delivering live video and voice over the network is that the data continues to flow quickly. Live video and voice applications can tolerate some loss with minimal or non-noticeable effect and are perfectly suited to UDP. The blocks of communications in UDP are called datagrams. These datagrams are sent as best effort by the transport layer protocol. The UDP header is far simpler than the TCP header because it only has 4 fields and requires 8 bytes or 64 bits. The figure here shows the fields in a UDP header. This includes source port, length, destination port, checksum, and application layer data. The table identifies and describes the four fields in the UDP header. As mentioned earlier, these are the source ports, destination port, length, and checksum. All of it on a 16-bit field. Applications that use UDP. There are three types of applications that are best suited for UDP. Live video and multimedia applications. These applications can tolerate some data loss but require a little or no delay. Examples include VoIP and live streaming videos. Simple request and reply applications. Applications with simple transactions where a host sends a request and may or may not receive a reply. Examples include DNS and DHCP. Applications that handle reliability themselves. Unidirectional communications where flow control, error detection, acknowledgments, and error recovery is not required or can be handled by the application. Examples includes SNMP and TFTP. Now the figure identifies applications that requires UDP. Although DNS and SNMP uses UDP by default, both can also use TCP. DNS will use TCP if the DNS request or DNS response is more than 512 bytes, such as when a DNS response includes many name resolutions. So similarly, under some situations, the network administrator may want to configure SNMP to use TCP. Port numbers. Multiple separate communications. As you have learned, there are some situations in which TCP is the right protocol for the job, and other situations in which UDP should be used. No matter what type of data is being transported, both TCP and UDP use port numbers. The TCP and UDP transport layer protocols use port numbers to manage multiple simultaneous conversations. As shown here in the figure, TCP and UDP header fields identify the source and destination application port numbers. The source port number is associated with the originating application on the local host, whereas the destination port number is associated with the destination application on the remote hosts. For instance, assume a host is initiating a web page request from the web server. When the host initiates a web page request, the source port number is dynamically generated by the host to uniquely identify the conversation. Each request generated by a host will use a different dynamically created source port number. This process allows multiple conversations to occur simultaneously. In the request, the destination port number is what identifies the type of service being requested of the destination web server. For example, when a client specifies port 80 in the destination port, the server that receives the message knows that the web services are being requested. The server can offer more than one service simultaneously, such as web services on port 80, while it offers File Transfer Protocol or FTP Connection Establishment on port 21. Socket pairs. The source and destination ports are placed within the segment. The destination are then placed or encapsulated within an IP packet. The IP packet contains the IP address of the source and destination. The combination of the source IP address and the source port number, or the destination IP address and the destination port number, is known as the socket. In the example, in the figure, the PC is simultaneously requesting an FTP and web services from the destination server. So in the example, the FTP requests generated by the PC includes a layer 2 MAC address and the layer 3 IP address. The request also identifies the source port number 1305, example, dynamically generated by the hosts, and destination port identifying the FTP services, port 21. So the host also has requested a web page from the server using the same layer 2 and layer 3 addresses. However, it is using the source port number 1099, example, dynamically generated by the host, and destination port identifying the web service on port 80. The socket is used to identify the server and the service being requested by the client. A client socket might look like this, with 1099 representing the source port number 192.168.1.5, okay? And then you've got 1099. Okay, so it's exactly like 192.168.1.5 colon 1099. The socket on the web server might be on 192.168.1.7, okay, colon 8. So together, these two sockets combine to form a socket pair 192.168.1.5 colon 1099, 192.168.1.7 colon 80. So sockets enable multiple processes running on a client to distinguish themselves from each other, and multiple connections to a server process to be distinguished from each other. So the source port number acts as a return address of the requesting application. The transport layer keeps track of this record and the application that initiated the request so that when a response is returned, it can be forwarded to the correct application. Port number groups. The Internet Assigned Numbers Authority, or IANA, is the standards organization responsible for assigning various addressing standards, including the 16-bit port numbers. The 16 bits used to identify the source and destination port numbers provides a range of ports from 0 to 65,535. So the IANA has divided the range of numbers into the following three port groups. You've got the well-known ports from 0 to 1023, registered ports from 1024 to 49,151, and private and/or dynamic ports at 49,152 to 65,535. So take note that some client operating systems may use registered port numbers instead of dynamic port numbers for assigning source ports. The table displays some common well-known ports and their associated applications. So something like port 20, that's TCP. Okay, 21 is also for TCP. You've got port 80 for TCP, 443 for HTTPS, and so on. So some applications may use both TCP and UDP. For example, DNS uses UDP when clients send requests to a DNS server. However, communications between two DNS servers always use TCP. So search the IANA website for port registry to view the full list of port numbers and associated applications. The netstat command. Unexplained TCP connection can pose a major security threat. They can indicate that something or someone is connected to the local host. Sometimes it is necessary to know which active TCP connections are open and running on a network hosts. So netstat is an important network utility that can be used to verify those connections. As shown below, or as shown here, enter the command netstat to list the protocols in use. The local address and port numbers and foreign addresses and port numbers and the connection state will be displayed, as shown here. By default, the netstat command will attempt to resolve IP addresses to domain names and port numbers to well-known applications. The -n option can be used to display IP addresses and port numbers in their numerical form. TCP Communication Process. TCP Server Processes. You already know the fundamentals of TCP. Understanding the role of port numbers will help you to grasp the details of the TCP communication process. In this topic, you will learn about the TCP three-way handshake and session termination processes. So each application process running on a server is configured to use port numbers. The port number is either automatically assigned or configured manually by a system administrator. An individual server cannot have two services assigned to the same port number within the same transport layer services. For example, a host running a web server application and a file transfer application cannot have both configured to use both the same port, such as TCP port 80. An active server application assigned to a specific port is considered open, which means that the transport layer accepts and the processes segment addressed to that port. Any incoming client request addressed to the correct socket is accepted, and the layer is passed to the server application. There can be many ports open simultaneously on a server, one for each active server application. So, information about TCP processes. So, clients sending TCP requests. Client 1 is requesting web services, that is port 80, and client 2 is requesting an email service using a well-known ports. Example, web services for port 80 and email services for port 25. Request destination ports. Requests dynamically generate a source port number. In this case, client 1 is using the source 49152. Okay? And client 2 is using the source port 5152. Request source ports. When the server responds to the client requests, it reverses the destination and source ports of the initial requests. Response destination ports. Notice that the server response to the web request has now destination port 49152. And the email response now has destination port, okay, so 51152. Resource source ports. The source port in the server response is the original destination port in the initial requests. TCP Connection Establishment. In some cultures, when two persons meet, they often greet each other by shaking hands. Both parties understand the act of shaking hands as a signal of a friendly greeting. Connections of the network are similar. In TCP connections, the host client establishes the connection with the server using the three-way handshake process. So step 1, the initiating client requests a client-to-server communication session with the server. Step 2, the server acknowledges the client-to-server communication session and requests a server-to-client communication session. Third, the initiating client acknowledges the server-to-client communication session. So the three-way handshake validates the destination host is available to communicate. In this example, host A has validated that host B is available. Session termination. So to close a connection, the finish or fin control flag must be set in the segment header. To end each one-way TCP session, a two-way handshake consisting of a fin segment and an acknowledgement segment is used. So therefore, to terminate a single conversation supported by TCP, 4 exchanges are needed to end both sessions. Either the client or the server can initiate the termination. In the example, the terms client and servers are used as a reference for simplicity. But any two hosts that have an open session can initiate the termination process. So step 1. FIN. When the client has no more data to send in the stream, it sends a segment with a FIN flag set. Second, ACK. Okay, the server sends an ACK to acknowledge the receipt of the FIN to terminate the session from client to server. Step 3, FIN. The server sends a FIN to the client to terminate the server to a client session. And then step 4, ACK. All right. So the client responds with an ACK to acknowledge the FIN from the server. When all segments have been acknowledged, the session is closed. TCP three-way handshake analysis. Host maintain state. Track each data segment within a session and exchange information about what data is received using the information in the TCP header. TCP is a full duplex protocol where each connection represents two one-way communication sessions. So to establish the connection, the host performs a three-way handshake. So these are the functions of a three-way handshake. First, it establishes that the destination device is present on the network. Second, it verifies that the destination device has an active service and is accepting requests on the destination port number that the initiating client intends to use. And then third, it informs that the destination device that the source client intends to establish a communication session on that port number. So after the communication is completed, the sessions are closed and the connection is terminated. The connection and session mechanisms enable the TCP reliability function. As shown in the figure, control bits in the TCP header indicate the progress and status of the connection. So this includes the 6 control flags: URG or Urgent Pointer Field Significant, ACK for Acknowledgement, PSH for Push Function, RST for Reset, SYN for Synchronize, and FIN for Finished or No More Data from Sender and used in a session termination. Search the internet to learn more about the PSH and URG flags. Reliability and flow control. TCP reliability, guaranteed and ordered delivery. The reason that TCP is the better protocol for some applications is because, unlike UDP, it resends drop packets and numbers packets to indicate their proper order before delivery. TCP can also help maintain the flow of packets so that devices do not become overloaded. This topic covers these features of TCP in detail. There are many times when TCP segments do not arrive at their destination. Other times, the TCP segments might arrive out of order. For the original message to be understood by the recipient, all the data must be received and the data in these segments must be reassembled into the original order. Sequence numbers are assigned in the header of each packet to achieve this goal. The sequence number represents the first data byte of the TCP segment. During the session setup, an initial sequence number or ISN is set. This ISN represents the starting value of the bytes that are transmitted to the receiving application. As data is transmitted during the session, the sequence number is incremented by the number of bytes that have been transmitted. This data byte tracking enables each segment to be uniquely identified and acknowledged. Missing segments can then be identified. The ISN does not begin at 1 but is effectively a random number. This is to prevent certain types of malicious attacks. For simplicity, we will use an ISN of 1 for the examples in this module. Segment sequence numbers indicates how to reassemble and reorder received segments, as shown here in the figure. TCP segments are reordered at the destination. The receiving TCP process places the data from a segment into a receiving buffer. Segments are then placed in the proper sequence order and passed to the application layer when reassembled. Any segments that arrived with sequence numbers that are out of order are held for later processing. Then, when the segments with the missing bytes arrived, the segments are processed in order. TCP reliability, data loss, and retransmission. No matter how well designed the network is, data loss occasionally occurs. TCP provides methods of managing these segment losses. Among this is a mechanism to retransmit segments for unacknowledged data. Prior to later enhancements, TCP could only acknowledge the next byte expected. For example, in the figure, using segment numbers for simplicity, host A sends segments 1 to 10 to host B. If all the segments arrived except for segments 3 and 4, as shown here on the diagram, host B would reply with acknowledgement specifying that the next segment expected is 3 or segment 3. Host A has no idea if any other segments arrived or not. Host A would therefore resend segments 3 through 10. If all the resent segments arrived successfully, segments 5 through 10 would be duplicated. This can lead to delays, congestion, and inefficiencies. Host operating systems today typically employ an optional TCP feature called Selective Acknowledgement, or SAAC, negotiated during a three-way handshake. If both hosts support SAAC, the receiver can explicitly acknowledge which segment or bytes were received, including any discontinuous segment. The sending host would therefore only need to retransmit the missing data. For example, in the next figure here, again using segment numbers for simplicity, host A sends segments 1 through 10 to host B. If all the segments arrived except for segments 3 and 4, host B can acknowledge that it has received segments 1 and 2, acknowledge 3, and selectively acknowledge segments 5 through 10, SAAC 5 to 10. Host A would only need to resend segments 3 and 4. So take note that TCP typically sends ACKs for every other packet, but other factors beyond the scope of this topic may alter this behavior. TCP uses timers to know how long to wait before resending a segment. TCP flow control window size and acknowledgements. TCP also provides mechanism for flow control. Flow control is the amount of data that the destination can receive and process reliably. Flow control helps maintain the reliability of TCP transmission by adjusting the rate of data flow between the source and destination for a given session. To accomplish this, the TCP header includes a 16-bit field called window size. The figure shows an example of window size and acknowledgement. The window size determines the number of bytes that can be sent before expecting an acknowledgement. The acknowledgement number is the number of the next expected byte. The window size is the number of bytes that the destination device of a TCP session can accept and process at one time. In this example, PCB, from the figure, initial window size for the TCP session is 10,000 bytes. Starting with the first byte, byte number 1, the last byte PCA can send without receiving an acknowledgement is byte 10,000. This is known as the send window of PCA. Now, the window size is included in every TCP segment, so the destination can modify the window size at any time depending on buffer availability. The initial window size is agreed upon when the TCP session is established during a three-way handshake. The source device must limit the number of bytes sent to the destination device based on the window size of the destination. Only after the source device receives an acknowledgement that the bytes have been received can it continue sending more data for the session. So typically, the destination will not wait for all the bytes for each window size to be received before replying with an acknowledgement. As the bytes are received and processed, the destination will send acknowledgements to inform the source that it can continue to send additional bytes. For example, it is typical that PCB would not wait until all 10,000 bytes have been received before sending an acknowledgement. This means PCA can adjust its send window as it receives acknowledgement from PCB. As shown in the figure, when PCA receives an acknowledgement with acknowledgement number 2921, okay, which is this one, that is the expected byte or the next expected byte. So the PCA send window will increment to 2920 bytes. So these changes will send window from 10,000 bytes to 12,290 bytes. All right. Okay. Now, a destination sending acknowledgement as it processes bytes received, and the continual adjustment of the source send window is known as sliding windows. In the previous example, the send window of PCA increments or slides over another 2,991 bytes from 10,000 to 12,920. If the availability of the destination's buffer space decreases, it may reduce its window size to inform the source to reduce the number of bytes it should send without receiving an acknowledgement. So take note that devices today use the sliding windows protocol. The receiver typically sends an acknowledgement after every 2 segments it receives. The number of segments received before any acknowledgement may vary. The advantage of sliding windows is that it allows the sender to continuously transmit segments, as long as the receiver is acknowledging previous segments. The details of sliding windows are beyond the scope of this course. TCP Flow Control Maximum Segment Size, or MSS. In the figure, the source is transmitting 1,460 bytes. That is within each TCP segment. This is typically the maximum segment size, or MSS, that the destination device can receive. The MSS is part of the options field in the TCP header that specifies the largest amount of data in bytes that a device can receive in a single TCP segment. The MSS does not include the TCP header. The MSS is typically included during the three-way handshake. A common MSS is 1,460 bytes when using IPv4. A host determines the value of each MSS field by subtracting the IP and TCP headers from the Ethernet Maximum Transmission Unit, or MTU. On an Ethernet interface, the default MTU is 1,500 bytes. Subtracting the IPv4 header of 20 bytes and the TCP header of 20 bytes, the default MSS size will be 1,460 bytes, as shown here in the figure. TCP Flow Control Congestion Avoidance. When congestion occurs on a network, it results in a packet being discarded by the overloaded router. When packets containing TCP segments do not reach their destination, they are left unacknowledged. By determining the rate at which TCP segments are sent but not acknowledged, the source can assume certain level of network congestion. Whenever there is congestion, retransmission of lost TCP segment from the source will occur. If the retransmission is not properly controlled, the additional retransmission of the TCP segment can make the congestion even worse. Not only when new packets with TCP segments introduced into the network, but the feedback effect of the retransmitted TCP segments that were lost will also add to the congestion. So to avoid and control congestion, TCP employs several congestion handling mechanisms, timers, and algorithms. So if the source determines that the TCP segments are either not being acknowledged or not acknowledged in a timely manner, then it can reduce the number of bytes it sends before receiving an acknowledgement. As illustrated in the figure, PCA senses there is congestion and therefore reduces the number of bytes it sends before receiving an acknowledgement from PCP. Acknowledgement numbers are for the next expected byte and not for a segment. The segment numbers used are simplified for illustration purposes. Notice that it is the source that is reducing the number of acknowledged bytes or unacknowledged bytes it sends and not the window size determined by the destination. So take note that explanations of the actual congestions, handling mechanisms, timers, and algorithms are beyond the scope of this course. UDP Communication. UDP Low Overhead versus Reliability. As explained before, UDP is perfect for communications that needs to be fast, like VoIP. This topic explains in detail why UDP is perfect for some types of applications and transmissions. As shown in the figure, UDP does not establish a connection. UDP provides low overhead data transport because it has a small datagram header and no network management traffic. UDP Datagram Reassembly. Like segments with TCP, when UDP datagrams are sent to a destination, they often take different paths and arrive in wrong order. UDP does not track sequence numbers the way TCP does. UDP has no way to reorder the datagrams in their transmission order as shown in the figure. So take note that in here, the sender were able to forward the datagram in order of datagram 1, 2, 3, 4, 5, and 6. But it was received out of order in 1, 2, 6, 5, 4 with datagram 3 missing. So with this one, therefore, UDP simply reassembles the data in the order that it was received, and it will be forwarded to the application in this fashion. If the data sequence is important to the application must identify the proper sequence and determine how the data should be processed. UDP Server Processes and Requests. Like TCP-based applications, UDP-based server applications are assigned well-known or registered port numbers as shown in the figure. When these applications or processes are running on a server, they accept the data matched with the assigned port number. When UDP receives a datagram destined to one of these ports, it forwards the application data to the appropriate application based on its port number. So UDP server listening for requests, as shown here in the figure. Okay, so take note that remote authentication dial-in service or radius server shown in the figure provides authentication, authorization, and accounting services to manage user access. The operation of radius is beyond the scope of this course. UDP Client Processes. As with TCP, client-server communication is initiated by a client application that requests data from the server processes. The UDP client process dynamically selects a port number from the range of port numbers and uses this as the source port for the conversation. The destination port is usually the well-known or registered ports assigned to the server processes. After a client has selected the source and destination ports, the same pair of ports are used in the header of all the datagrams in the transaction. For the data returning to the client from the server, the source and destination port numbers in the datagram header are reversed. The figure illustrates two hosts requesting services from the DNS and Radius authentication servers. So clients sending UDP requests. So client 1 is sending a DNS request using the well-known ports, port 53, while client 2 is requesting a Radius authentication services using the registered port 1812. UDP destination ports. The requests of the clients dynamically generate source port numbers. In this case, client 1 is using source port 49152 and client 2 is using source port 51152. UDP request source ports. When the server responds to the clients, it reverses the destination and source ports of the initial requests. UDP response destination. In the server response to the DNS request is now destination port 49152. And the Radius authentication response is now destination 51152. UDP response source ports. The source ports in the server response are the original destination ports in the initial requests. So we have reached the end of this video lecture. So I hope you learned something from this new lesson today. Have a great day.